microphone work? Okay, great. Yes, so here I want to talk about how to detect gravitons. I'm very excited about this work, which just came out a couple of weeks ago, basically because it was considered impossible until recently. And in fact, I also thought it was impossible, but it turns out it's something that has been mostly overlooked in light of modern experimental capabilities. So I'm going to guide you through it, how graviton detection is actually realistic, still hard, but completely realistic. Okay, so let me first, let's see. Right, let me first ask, especially in the spirit of this conference, there's of course the question of what can AMO physics and low energy physics tell us about fundamental physics? And most of the questions that usually studied in this field are related to this pie chart. Okay, so there is the big questions about dark energy, dark matter, or maybe other kind of fundamental particles that we don't know, or questions that we can summarize here. Now, the good thing about it, though, is that we can make a chart like that. So we do have evidence that there is some kind of open questions that exist. Okay, so what fascinates me is a slightly different question. It's of this form. Namely, what can we tell about the quantization of gravity experimentally? And that is a completely uncharted territory in the sense of there's no experimental evidence whatsoever. Okay, there's a little bit of things like short range Newtonian physics or maybe some other small experiments, but nothing of the sort like what we have here. And so this is a field that I started working on since even as my undergrad 15 or close to 20 years ago. It's been growing steadily, which is very exciting, and especially has been growing steadily experimentally. Because it turns out there's actually a lot of questions that we can ask and answer experimentally, which seemed kind of counterintuitive even until a few years ago. So here I want to add to the mix with also novel capability, just showing that we can detect gravitons and we can also explore this type of questions in real world experiments. Okay, so let me just say a couple of words since this is an ITAMP conference. It's very exciting for me because this work started at ITAMP when I was here as a postdoc. And I was working a few years ago with Shimon, Misha, June, and Ron on questions such as how do you detect gravitational waves with modern quantum systems, in this particular case with atomic clocks. And the trick there is to leverage quantum control of these systems, such that you can really actually measure something different. And this work was started even before the first LIGO detections. So it kind of seemed far off, but then it became much more interesting because gravitational waves actually were confirmed while we were working. In parallel, I was also working together with Swati Singh and Keith Schwab on a different type of question, also related to gravitational waves. Could we use optomechanical systems also to detect gravitational waves in modern waves? And here, similarly, you leverage a different type of quantum technology, in this case, a superfluid helium, and then you basically have an extremely stable and resonator, which resonates for an extremely long time because of very high Q, and then you could measure it. Now, one question I was asking myself then in this time, kind of more of my daughter was born, so I didn't have time to do much, but just to think random stuff. And so the question was, could we actually think about single graviton processes in these things? And this seems in principle preposterous because single graviton processes should be rare. However, if we have such a system, it has a very large mass. Okay, and not only that, it also has quantized levels. And so could we just prepare such a system in an excited state and then wait for a quadrupole transition to occur? And the essence of that is, yes?
Can you turn off the background blur on your on the video? Apparently it's giving some weird effects.
It's okay. It's a blur. Okay. All right. How about that? Oh, great.
Sorry.
Yeah, that's quantum noise. So the question was simply, can we use macroscopic quantum systems and still measure in a quantum domain and then say something about gravity? And the upshot is basically, yes, you can do that. And A, it works, and B, it's actually relatively feasible. It's still hard, but it's relatively feasible. Okay, now this is the overview of my talk. I want to say just a couple of words of the, just my group that we work on gravity quantum interface. It's kind of like an AMO physics, low energy approach to fundamental physics, mostly focused on questions related to gravity. And the reason I want to say that is because we have like postdoc and PhD positions. So maybe you can then let others know who might be interested. And then I'll talk a little bit about what's the difficulty in detecting gravitons and what have other people considered. And basically, what is the solution, how you can actually do it. from resonant interactions. I'll talk a little bit about experimental feasibility, and then also limitations of this and interpretations, and what we can in principle learn about linearized quantum gravity from such detections. Okay, so so first, just like a little propaganda slide about the group. We're focused on quantum optics and information theory, with like bread and butter quantum information, such as quantum control of novel quantum systems, such as optomechanics, or here quantum metasurfaces, or just other interesting phenomena that pushes quantum mechanics into new domains. How do you measure and prepare quantum states there? How do you use it for quantum sensing? What can it be good for? And then particular applications like gravitational wave detection, quantum sensors for that. Also questions related to cosmology, but like a low energy approach. Namely, are there some interesting kind of quantum phenomena that might arise in cosmology, such as squeezing? And the answer is yes, it does actually arise there. And then here on this side is questions related to gravity. Namely, what kind of experiments could we potentially do to probe some questions related to the interface of quantum theory and gravity and phenomenological models? How does gravity affect quantum systems and their dynamics? What are in principle even like Gedanken experiments and things that we can even tell about gravity? Do we need to quantize it or not? And it turns out actually you don't necessarily need to. It works well to quantize it. It's a theoretical statement in the linearized regime. But whether you have to or not is, it's not answered. It has to be answered empirically. And in contrast to the electromagnetic case, there's no necessity to do that from just pure Gedanken experiments so far. And then same with gravity signature. Now, just one quick slide on this area, because I work on that quite a bit. I just want to say like one example has nothing to do with quantum gravity, but it's the question, hey, if you interfere clocks, which is kind of more suitable for this audience, are there new effects that arise? And it turns out, yes, you can actually probe the effect of curved spacetime in quantum theory with quantum phenomena related to clocks. And so you can look at new entanglement generation through spacetime, the curvature and proper time interference. There's the coherence effect that arise. And we have some ongoing collaborations with different people like Shimon, June, and Christian Zanger as well, on just different aspects of this. So what kind of experiments could we do that could tell us some kind of empirical evidence on how gravity and quantum theory meet deeply in the GR regime or in some relativistic regime and purely quantum mechanical at low energies. So you don't need to do field theory for that. And so there's questions such as what are quantum features of proper time? How do you witness some time relation-induced entanglement? And could there even be some quantum gravity signatures in this? Okay, so I mentioned that as I was mentioning, just because to say like we need to expand a little bit. So if you know any candidates for postdocs or even PhD students, just let them know. Okay, and right, and this is at Stevens, which is just across from this is nearly a picture from our campus, but it could have been. It's just across in Hoboken across Manhattan. Okay. Now, let me focus on the main thing I wanted to talk about. I hope I haven't run out of time yet. I want to put it a little bit first in the context of what people do consider for a type of experiments to test quantum gravity. Okay, one class of experiments is to test phenomenological speculative models. Okay, there's many proposals in the last 10, 20 years about it, such as measuring, is there some fundamental collapse? Does quantum coherence stop somewhere due to gravity? Or is there some change in the Heisenberg uncertainty principle? That was something I worked on 50 years ago. Bekenstein had also proposals about quantum foam. We can test all these things in tabletop experiments and constrain them. There's classical models for interactions and so forth. So there's many models that we can test, but they're all speculative. So we basically just rule them out. And if you believe quantum theory, none of them should be true. Okay. But it's still important to basically do the test. It's no different, in fact, I think, than testing for some random dark matter particles that probably are all wrong anyway.
I disagree.
That's right. No, it's true. Only mean because we've been looking for so long. So, I was sharing Amar's frustration. So the second aspect is actually let's look at quantum gravity as predicted by normal physics, but in the low energy limit. And one famous class now of these experiments proposes to look for entanglement that's generated by gravity. And so there's an interesting test where you create source masses which are quantized, and they gravitate. And then you look what happens. And so you can learn something about gravity, but with some ambiguous interpretations. So actually there, you cannot use it to tell, really to tell something about kind of also, aspects of quantum gravity. All you're telling is that, superpositions gravity. And then with additional assumptions, maybe you can deduce some other things, but it's all ambiguous. And here I want to say this is a different class essentially of experiments that we are here suggesting, which probe something different, not superpositions. There's absolutely no superpositions that is relevant. There's absolutely no source masses of gravity that have to be quantum, but instead we're looking at a single exchange of quanta between gravity and matter, and you're zooming into on that kind of aspect of the quantized interaction. Okay, so it's a completely different limit with different challenges and opportunities. So it's an observation of quantized exchange of energy. And basically what you do is you probably expect that single graviton physics from linearized quantum gravity. And of course, there's also a caveat, namely this experiments alone cannot, they cannot prove quantum gravity, but they cannot exclude some semi-classical alternative. But it's a different type of experiment with different type of opportunities and challenges. Okay, so now let me dive a little bit into the history of this. Can gravitons be directly detected? And this usually the conventional answer is no. A typical example is look, LIGO is hard enough. Okay, so LIGO is extremely hard, took 60 years to build. They finally did gravitational waves. You can calculate how many gravitons would you expect there, something like 10 to the 36. So the naive answer is you want 36 orders of magnitude improvement to detect gravitons. That's usually where they kind of where it starts, and also the arguments end, kind of like, okay, you can't do it. All right, so that's true, you can't do it, so you shouldn't use LIGO. Then you can look at graviton, well, at least not in this way. Then you can look at the single cross-section between, just atoms and gravitons, and you can compute what is their scattering strength. And it's extremely weak. It's something like on the Planck area, so it's also extremely weak. Or if you think of, energies you might need, it's all just seems kind of science fiction. So the typical answer is no, you can't do it. But it turns out it's incorrect. There's something that's been overlooked. You can actually do it. And the trick is this. In some sense, I can give you the upshot. Here, this is the mistake. Graviton atom interaction is very bad. That's true. But graviton mass quadrupole interaction can be very big, because you can have a system which is not an atom and still quantized. And that's all there is. Okay, so let me also go back a little bit in more detail what people said, because sometimes I realized I have the feeling, especially quite in field theory community, there seems to be a perception that somehow we're playing here semantics or something like that we're not talking about real graviton detection, but something else. So I just want to contrast this, exactly the same as everybody else ever talked about. Everything is exactly the same. There's absolutely no reason. We just show it can be done. So here, for example, Dyson, when he concludes you can't detect gravitons, one of the ways that he analyzes it is by using a graviton detector, which is an electron and an atom, and then it waits for external gravitational waves to appear, external gravitons, such as thermal gravitons here. And he looked at, for example, thermal gravitons coming from the sun. He concludes, you can't do it with an atom. And he calls it a gravitoelectric detector, basically for kilovolt gravitons. Or by Rothman-Bond, which have a series of very beautiful papers on this topic, they basically define graviton detection as the radiation analogy of the photoelectric effect. Okay, you have a detector, it's a big source, click. That's what the graviton detector. Okay, so they look at this graviton ionization cross-section for hydrogen, and then also conclude, look, it's just too weak. But the principle is exactly the same as what we're doing. Now, so the two key points of what we mean by graviton detection, because it can mean many different things. We mean a discrete exchange of energy, E equals HF, and it's extracted from some background. So there's some kind of source, and you extract a discrete amount of energy from it. And it's exactly the same spirit as before. Okay, and so actually I have to be careful. I don't know how much. Yeah. Okay. So I'll just go.
I'll give you 5 minutes.
You give me a 10 minutes.
10, I'll give you 10 minutes.
Right. So just a very quick, another historical thing is that it's beautifully written up in actually Weinberg's book on gravitation. And that's what I was reading here back as a postdoc trying to understand it. He talks actually about just, single graviton transitions. And again, this is linearized quantum gravity. We can just use it. There's absolutely nothing special theoretically. It's just an interesting experimental question. And theoretically, it's exactly the same as, a dipole approximation electromagnetism, except we use here quadrupoles. And so you can compute just transition rates. And so he does that, for example, in an atom, produce a quadruple transition rate, and he gets a number which is incorrect, but Von and Rothman just revisited it. He just plugged in the numbers wrong. And so you get something like 10 to the minus 40. So it's an extremely small number, but you can just compute it. So it's basically you have an atom, then you have a quantum jump because of a graviton. What's the rate of that? It's tiny. Okay, so he says, needless to say, there's no chance of observing a transition like that. Okay. And now, how does it proceed? Just very quickly, just to show like there's nothing mysterious about the math. You have some fundamental interaction Hamiltonian in the linearized limit, where you couple matter to the perturbation, radiation wave perturbation. You can assume something, for the matter distribution, like a single electron and a potential in this case. Then you plug in this metric for the gravitational wave, which is just decomposed in typical Fourier because it's all linearized. That's fine. It's just Fourier components. And then you can quantize the gravitational perturbation, just by linearized. That was done first by Bronstein 90 years ago, actually, exactly. That was one of the first and last things he did, and then he was executed by Stalin for no reason. But he had time to invent quantum gravity. This is basically how you do it. You quantize it, and then you can just plug it into like transition rates. You can just look at probabilities of different processes from this interaction Hamiltonian, such as going from 0 to 1 with some density of states. And anyway, this is how you get it. Just plug in here. The states are these quadrupolar wave functions. So you just get the numbers. I mean, just to quickly run through that. There's nothing extremely complicated. You don't need string theory, so it's basically AMO physics. And so you get the rate. Okay. Now what we did, now I want to come to our work actually. So what we did is just a few modifications to that in terms of what type of physical scenarios you should look at. Okay. And one is, first of all, let's go away from atom, because you always think about atoms when you think about quantum mechanics. But of course, today in AMO physics, we know that's not true. We can talk about macroscopic systems and still measure quantum states and prepare quantum states of them. And that's the key, because this couples to the mass quadrupole. And so let's look at acoustic modes and other electronic transitions in macroscopic quantum systems. That's A. B, let's focus again, like they did, on stimulated emission. So you have like some gravitons coming through. We extract some of them probabilistically, but now we know the source because we have LIGO. So we actually know exactly what's coming. We know it's coming all the time and we detect it. So we can use the exact numbers from LIGO, from the gravitational waves that actually pass us and we detect. And then finally, what you need quantum sensing in the sense that you want to look at the ability to really measure QD measurement of discrete transitions in energy, because that is what E equals HF is, the discrete energy level. So you want to measure them. And this is, of course, the bottleneck versus, in other proposals, you have the superpositions, how they do that. Here you have to do quantum sensing, which is, I think, much easier, but still a hard challenge for macroscopic systems. So you just want to see this discrete transition. And the point is that you need all three. You can't, neither one of us alone will be sufficient, but if you have all three, then you have a single graviton detector, this will show. Okay, so let's go through these just quickly. Okay, I don't want to go into detail. One thing I want to say, we just build up the detector from first principles, just for the reason to make sure that we do nothing wrong, because we know how to quantize atoms. And so we don't want to quantize, some kind of macroscopic system. So we just build up a big system out of n atoms, and we wanted to see how the scaling proceeds. It's a computation in our appendix. Just basically, you take n atoms and you look at the interaction with them, and then you find collective modes. You just express instead of n atoms the collective modes of the system that you change. And there's two things that arise, and it's really beautiful. You get one term which is tiny. So you have n atoms, you have like total mass that comes in, but it scales as something like quadratic in your tiny displacements. But you get another, and this is the subleading term, which basically everybody else focused on. But you get another term, which is essentially the fact that you have a fractional change due to radiation waves. And this other term scales with the total length of the system and with the mass. So you get an enhancement, but not just by the number of atoms, but the number of atoms squared that go in. And that has simply to do with the fact that you're dealing with a mass quadrupole. So it's not additive. It's quadratic. So you get mass times L. And this term is, in fact, very well known. All bar detectors use that. So we're just accidentally reinvented the wheel, but it's basically you just wanted to make sure you quantize the right degrees of freedom. So you quantize these modes, And then the dominant interaction term is the one that scales with mass, scales with length, macroscopic. And then you couple basically your gravitational wave perturbation to the quantized position of the system. Okay, and then you can look again at what are the transition rates, just to run some numbers. Okay, you can just plug it in and you get some macroscopic quantities like density and length and sport. So you can just plug in some numbers like a typical Mars they had long ago. And for example, you can ask the question, what's a spontaneous transition? I was hoping that's going to be big, but it's not big. It's very small. Still like 10 orders of magnitude better than Weinberg, but it's it's very small. So you can't do spontaneous emission. Okay, but then you can do stimulated one from the sources that we know that exist. So not like some thermal sources, but from the sources that we know exist. Again, sorry, I'm rushing through. It's just algebra. You plug in numbers and you get some number for a stimulated transition rate, which now depends on the macroscopic mass, speed of sound of your system, and that's it. L is just the mode, so you just look at the fundamental modes. This is best, and H is the amplitude of the radiation wave. Okay, and then if you just take some random example, like Joe Weber had like these bars, which is essentially this. You plug in something like 2 tongs, and you take the first radiation wave ever detected with this amplitude. What you get is that actually the stimulated rate is 1 hertz, which means that per second there's on average 1 graviton exchanged resonant. So here you have a resonant interaction where you really absorb and emit energy. So it's not off resonant like in LIGO, but it's really a resonant exchange because you have to be in resonance here. And it proceeds at pretty good rate. So in some sense, the only reason you could think of detecting gravitons is because it interacts so weakly. It is so weakly interacting that even if you try to detect it, you actually only get a few gravitons. So even if they were successful, on average, they would probably also only see 10 or 100 gravitons. So it's just to see how the numbers go. Of course, these rates are irrelevant for us because these rates tell us nothing about discrete exchange of energy. Just as a side note, this is basically the analogy of a photoelectric effect. Okay, so you have like a big classical source, and then it deposits energy, and what comes out is some discrete exchange of energy. Okay, so that's what here we are. Then you conjecture, look, maybe the radiation field is discretized as well. So it's basically the same thing that you have like you get exactly the same dependencies as well as in a photoelectric effect. So you just have something that depends only on the frequency. Okay. But the point is that what we do want to see, like we don't have an atom or something else, we want to see is really this discrete change of energy and not some kind of average rate. And so what you need to do is you need to make a measurement of just a single event probabilistically. You don't want to average it because any number can come out, but you want to post-select on just a single event. And even worse, these radiation waves are not continuous and they change in frequency and so forth. And so in order to see discrete events, we want to basically monitor, do a QND measurement and monitor essentially a quantum jump in your detector with a well-defined specific discrete value and only one, and not like some kind of average flux or something. Okay, and so, my student called it gravitophononic effect, and that's pretty accurate. Okay, and now the issue though is now we have to solve it actually correctly. So now is the real work, and I just going to mention it, namely, because all these gravitational wave profiles are complicated, you can't do Fermi's golden rule, and it changes in time and frequency. And so, for example, also going back to Andrei's talk, the best source for us that turns out to be is actually this neutron star merger that was detected 2017. And of course, the key thing about it and all of them is that they
might be muted.
Oh, let's see. Oh, it doesn't even let me.
Your sound might be muted, or maybe
It's probably muted.
well,
Yes, exactly. It will be. Thanks. Yes, exactly. Yeah, you can simulate gravity. It's pretty easy. Yes. Right. So this thing goes whoop, and it's basically a chirp. So the frequency goes up, and then it just dies off. So there's like all this dynamics that goes in, and you have to take it into account. And so basically, we just just need to solve the problem exactly, and you can because it's just 2 linear harmonic oscillators, so you can solve it exactly. So you look at this harmonic, basically just go back. You look at this interaction Hamiltonian. You can solve it. In fact, we can assume a very large, input for gravitational waves, And it's easy to solve. It's exactly the same, in fact, as Glauber's original computation. What you get from this Hamiltonian is essentially a displacement operator. So what the gradation wave does is it applies a displacement operator onto the acoustic mode with a certain strength here. Okay, and then with this, what you need to do is you need basically, if you ground state cool the system, so you have a massive system, you cool it to the ground state. When a radiation wave passes, it excites it into some coherent state with amplitude beta. And then this beta depends on all these parameters of the radiation wave, which is captured by this chi. So it's a changing wave and the frequency and all that, but it is all captured with this parameter as well as system parameters. And then what we want to look at is to maximize not the signal, but only the transition to a single excitation. Okay, so we just want to maximize this probability from 0 to 1, and it's maximized exactly when this beta parameter is exactly 1. Okay, and then you get a maximum probability, which is still like only 37%. So your ideal detector would be able only to detect it every third radiation wave, essentially. But the question is, what system parameters do we need to get an ideal single graviton kind of quantum jump detector? And that depends on the profile of the radiation waves as well as the mass and frequency of your detector. And so now we went and you can just scan live or whatever they detected and then plug in and see what mass we need depending on what radiation wave profile there is. And so the essential idea is, look, you ground state cool some massive system, you wait for radiation waves to come, you wait, and then there's like some change in discrete energy, and you measure it. And ideally, you would operate such that it's with 37% probability, and then you calculate it what it is. So you find an optimized mass, just inverting it. You find an optimized mass, and so for each radiation wave profile, we just found an optimal mass. Okay, and so this I just meant, chi just depends on all this different stuff about the gravitational waves. You can actually analytically approximate it as well for some cases, but that doesn't matter. Now the point is here, so then you use it for many different sources. Some sources are from LIGO detections, like black hole mergers, neutron star mergers. Some sources are just some speculative stuff that maybe could be there due to dark matter or primordial black holes, something like that. And so you have this high frequency stuff. But the point I want to make is that for most things, unless you go into speculative sources, for most detections that you have at LIGO, you need like ton scale detectors, and then you need to do quantum sensing there. And that's not, it's better than Weinberg, but it's not extremely realistic. However, it turns out there are some beautiful sources for which it works really nicely. If you choose beryllium, which they were planning to build anyway at some point, before they were shut down of these Weber bars, and you use this neutron star merger that they observed, if they had a detector around the 10 kilogram at that time, then there's a 30% chance, 37, they could have detected single transition from that source. But you need to suppress noise, but so you need like a millikelvin cooling, which is challenging, but it's also it's not not like femtokelvin. Yeah, thanks. Because these are the numbers you would expect. When you talk gravitons, you have to jump into a black hole or something like that. But these are all just kind of extremely challenging, but the reason why Q factor, so it's everything is maybe a factor 10, 100 beyond what people were considering. Okay, and so here this is actually just a comparison. This is just, it was fun to browse actually what people did with these bars, and then they're all shut down and what they imagined to do. And they were actually not too far from these lines is what you would need basically in terms of sensitivity if you wanted to use it as a gravitational wave detector. But it's an extremely bad gravitational wave detector because you only want to have one transition. If you have like 100 transitions, you don't want that because you get into like, you can't resolve anymore. So you basically want to build a bad gravitational wave detector, but resonant one. And you need basically noise suppression and Q factors is about factor 100 or so better, or 1,000 to what they were actually building, like mini Grail and so forth. Okay, right. Okay, so just as a comparison in terms of this technology. So that's not the bottleneck, it's hard. The real bottleneck is the quantum sensing part. So there's beautiful experiments in ETH just recently. I think they were measuring phonons, single phonon transitions and phonon counting on something like milligram scale. And so here, this is kilogram scale. So actually you could go from kilogram to gram scale as well with transducers. So still, there's a bit of a jump, but it's the sensing challenge. Okay, and so Right, so this is the final thing I want to mention is the sensing channel, which namely you need Q&D measurements of energy. And okay, you can model, like you will basically need to monitor, you don't know when the radiation wave comes, so you want to monitor it. If you had Lisa, they could tell you, but with LIGO, you never know, so you have to like monitor it all the time. So anyway, we just modeled it, how would it look like if you have like weak measurements and you monitor and you have some duty cycle. It's just simulations, basically, you would sometimes succeed or not, sometimes there's events coming or not. So you would see something like here, this green line, a pink line is like there's a wave passing, and so then your probability of being in the ground state drops to 0, and you get like this weak measurement over time tells you, okay, you were actually now in an excited state. Something like this. Okay, but let me just summarize this part. So you have ingredients such as you have macroscopic quantum system, stimulated single gravitons with correlating to LIGO, and quantum sensing of quantum jumps. And then for some events, the numbers are relatively reasonable, such as kilogram scale systems that you need to ground state cool, maintain, and measure. And then I want to measure, you could lower mass, so there's, more ideas, you can start thinking about it. Can use transducers to lower it further. There's also beautiful alternative, actually, suggestion to in a high frequency range, you can look at completely different processes. They could also be actually very relevant, such as conversion into gravitons from magnetic field. So this is work by Dan from the same time. Okay, so in principle, you can do it. Now, I want to mention like this interpretation and some issues that is important to keep in mind and know. Now, can we use this gravity detector to prove quantum gravity? And of course, okay, first of all, you heard Dan's talk, so of course you don't know. Second of all, we're all in physicists, so of course not. So we know just photoelectric effect alone is not a proof of all of QED. Okay, so you cannot use it to prove that gravity has to be quantum. Okay, that's clear. In particular, there's a particular semi-classical model that can reproduce it. Okay, there's this particular semi-classical model that can reproduce it. And so we can't distinguish those two. You need other experiments to do that. Anti-bunching, some Poisson statistics, or maybe negative Ingerfeld Bell violations. There's like a whole range of experiments we do today about QED that tell us more. But what I want to stress is these are kind of, higher order questions. Namely, the question is, can we distinguish it from this model? But that's not the only question that is interesting to ask. Namely, distinguishing from this model is somewhat pathological, but it's a limit of QED. So we want to exclude it eventually. But it's not maybe the first questions you want to ask about it. Namely, you can just ask other questions here or probe other models. Okay, this is not classical gravity. Okay, so this is a particular semi-classical assumption how classical and quantum systems interact. This does not follow from classical gravity in any way. Okay, so this is just some toy model that is good to exclude. Okay, so this semi-classical is not unique. There's other hybrid quantum classical interactions. People work on that, like the Oshie model or something, and they do not reproduce this, but they will violate that in some form. So you can ask some questions that you can answer about it. And in particular, this one we know arises if you have coherent states initially from normal physics, like in QED. We don't know actually if we have coherent states of gravitational waves. And so I don't know. Anyway, so there's there's still input that you can tell also about the radiation. And yeah, like I want to say, this does not arise from classical theory. So thank you. It's a good toy model, but this test cannot exclude it. So that's what it is. Okay, but here the goal is not to exclude it. The goal is really just to detect single quantum. Just to say, look, we can detect them. We can zoom in on what quantum theory predicts, and we're in that regime, so we can see clips. Okay, and so that brings me about a final question just in the last 2 minutes. It was just a fun exercise. We thought, what could we learn about quantization of gravity if we imagine we never knew anything about quantum optics? And in fact, that was the case before 1960s. And all of quantum theory was developed long before that. Nobody was doubting that QED you need long before we had any anti-bunching measurements. And so in particular, we looked with 3 clever high school interns that joined the group. And it was great because they never heard anything about quantum theory. So what we did is we looked at old papers. What convinced Einstein, Planck, Bohr, and others in the first 20, 30 years of quantum theory that you actually do have to quantize electromagnetism? And it turns out I didn't know, for example, Bohr really didn't like the photon. He really didn't want to have it, even after the Compton effect. He didn't want to quantize electromagnetism at all. But he came around. Einstein also didn't believe in the photon for a long time, but he realized you can't build any model. So you can build a semi-classical model, but it doesn't conserve energy. You can't make a meaningful model that's not pathological, other than E equals HF on both sides. That's the only model that works in a way that's consistent. So they couldn't come up with any alternatives, so they were convinced. First of all, lingering question still, but it was basically, a higher order. So we wrote this little essay, which, was nice. It won a little, just honorable mention. And we used it as inspiration, just to highlight, hey, what kind of tests could you do if you build such a detector? What questions could you ask? Very simple ones that we usually don't think about in quantum optics. Okay, and basically what we do is we probe this interaction. And we ask questions about it. So the first one is, for example, is the quantization of gravitational waves actually the same as everywhere else? Is Planck's constant the same for gravity as it is for matter? So it might be that you quantize it, but you have an anomalous graviton. Maybe it just gives you 2E or some other transition. So it will be completely consistent with every measurement we have so far, but it could be that the quantization proceeds a little bit different at the fundamental level. So you can test if H bar is the same for gravity as for matter. You can also check is actually if on the quantum level it's universal. You can build different detectors and then see if it's material dependent. That's what Millikan did, for example, and others at that time to see if these constants are universal. You can look at if there's a symmetry, if stimulated emission and absorption are on the same rate. Because that's also kind of fundamental principle from quantum theory, but might not be necessarily true. Or you can ask even, is this fundamental on a quantum level, a spin-2 transition? Is it really a quadrupolar transition we expect? Or is it some anomalous excitation that you get? So just simple things like that, they're not models that we want to probe, but it's, you can explore this linearized limit of quantized gravity and ask questions if things are as we expect. Okay, right, and then you can do multi-messenger thing there. Maybe what if you have this and a superposition experiment? Probably from both you can learn a lot. Because you're basically probing different aspects of this interaction. Okay, now with that, I just want to summarize. So single gravitons can be detected, and the point is you can use macroscopic objects that have acoustic transition, high mass, but also quantized. You need QED sensing, which is the challenge. You can cross-correlate with LIGO if it's in the right frequency band. And in fact, the fact that gravity is so weak is actually an asset. It's not, it's a feature, not a bug. That's a good thing, which is a bit counterintuitive. And so the upshot of that is, Dyson's conjecture that you can never detect gravitons is wrong, not true. And what turns out, this combination of these gentlemen would work, as well as, neutron star merger to the rescue. And so this is not a proof that we must have a quantum theory of gravity, but it's would be an exploration of what quantum gravity does predict at this thing. So you can explore linearized quantum gravity like it's 1905. Okay, now with that, let me thank, of course, all the people who did all the work. And so this is the main paper, and there's two small follow-ups. And yeah, thank you so much for your attention.
Make sure I understand what you said. So from your steps B and C, it looks like you create the coherence state of your detector and you project it onto the N equals 1 number state. Sounds to me like you're not detecting quanta of the field at all. Sounds to me like you're basically shaking it oscillator and projecting it onto the N equals 1 state. Let me rephrase. Imagine doing this with applying a classical acceleration to a pendulum. Put it in a coherent state, and you can project it onto the N equals 1 number state of the pendulum, and then you would say the same kind of physics. So yeah. I don't think you're in any way measuring quanta of the field. I think you're detecting quantum jumps of your detector, which would be kind of interesting in itself, but you're not necessarily detecting quanta of the field.
Yes, you do for the following reason. You have a resonant exchange of energy. Then and only then. If you have an off resonant excitation, then not. But if I shine a weak laser onto, I do a Rabi socket, something like that. Then for that to work, the only way it can work is if it's resonant, is if I absorb a single quanta of energy. So the quanta of energy has to come from somewhere. Okay, so here you're shaking it, so you're putting energy in, and so, you know, as you excite the energy, your arm will have, you know, will do work. And so here, work is produced by the gravitational wave. And if energy is conserved, you absorb the gravitons. And that's what linearized quantum gravity predicts from this, what's it? Right, so from this. So you're in the typical rotating wave approximation, and you have a beam split interaction. As soon as you have a click, you can compute what is actually my measurement operator. If I click and see a single graviton, it's exactly the one that is the, absorption of a single quanta from the field. Of course, you don't measure it directly, but you just have a click. I mean, it's the same as I shine a laser on my single photon detector, and it does click. It will click if and only if it had absorbed E equals HF.
But I think you see the clicks even if you classically accelerate with a sinusoidal acceleration, you're oscillating.
Yeah, but then you absorb the energy from something else, right? So here the point is you only absorb the energy from your resonant gravitational wave. So it's exactly the same as in a normal photodetector, just with a low probability.
It seems the detection is trying to detect a single quanta jump. And why is it necessary to cool down the whole stuff to ground state? Let's say if I keep it in the thermal state and detect the quantum jump, then that might still do the job, I guess.
Yes, it will still do the job, yeah. Just the cooling is not the hard part, so it was kind of just easier. But you're right, the cooling is irrelevant. You want to see how your energy changes resonantly. So you need to cross-correlate with LIGO to know that it was the right frequency, and it changed by just one quanta or any discrete amount of quanta. In resolve 10 on top of room temperature, that's great. But yeah, but ideally you would ground it, cool it, and see one excitation, or prepare first, second excited state or something. Yeah, so it's really just a change. You just want to see dynamically how it changes, cross-correlated with the fact that it had to be a resonant exchange.
One last question, yeah.
For the last second box, it doesn't like a curve, this is the point that can actually during this amplitude of your tiny light until there is a pressure. If sunlight in this like radical and two ways, they are coming like without any. How do we know we are imagining something that is average? Or well, if there's some ways that we can create like this amount, a little amount of something, see something, maybe that's possible.
Yeah, let me answer it in two ways. So, there are some standard features of the photoelectric effect, none of which really prove quantization. So, but there are some standard features which are strange. In normal classical physics, doesn't know what to do with it. And so exactly, it's this kind of intensity independence until some frequency threshold, and then it will grow linear with frequency. You have exactly the same response here. So let's say you could sample it from many different sources. So you can't create a source gradation wave, but you can look at for which does it actually respond. You would see the same thing. The response function is exactly the same. You see the same thing that until you hit a resonance, it doesn't matter what amplitude you have. And then only out from a specific frequency, then it grows with frequency. So you see that, but I just want to caution that it's still not a proof of quantization because there's still some semi-classical model, but they're pathological. So, but this is at least, this is contradicting normal classical theory interacting with the classical system. Yeah, but you get exactly the same response here. You just maybe need any detect.
Thank you very much. Thank all the speakers. And